Hello and good day to you. So I'm not using the Kaggle data this time, and I'm going to try and expand on the hypothesis testing that I showed you last time. My reasons for doing so is I'm trying to build a better understanding of the hypothesis testing methodology, because I feel that there's a tripwire in this, in that you can just think, I'm just going to run this hypothesis test. R's going to tell me what the percentage is like to be true. That's good enough for me. And if you think that, well done. That's what we want. But I would like to introduce a bunch of caveats and different ways of thinking about it, which can expand on it, and maybe you get a bit more utility out of a hypothesis testing. So in this case, I'm not using the Kaggle data. I'm using two random vectors produced by rnorm, producing a 10 and 20, mean of 100 and 105, and standard deviation of 5 in both cases. Now, if you're quick, you'd probably be able to realize that is likely to have a low probability value, and you're probably going to reject the null hypothesis. As you can see, you've got a p-value of less than 1. You're going to come away from that thinking, that you're safe to accept your hypothesis and that it couldn't happen by random chance. But you do have this additional piece of information within R of the DF. DF stands for degrees of freedom. Now, if you had a really high p-value, because I've ran that random number test a couple of times, and you can get a p-value where actually it's really high, even though it's really unlikely to get that value as a random sample, because we know these are producing random numbers in this case. But it can happen, and it's worth thinking about. We said previously that 5% of science and university data might be wrong because our p-value is around 5%. It doesn't matter in the long run, because tests should be recreated and repeated. But imagine that. Imagine a lot of data that comes out of universities might have problems, and the number of data that could be wrong, it might even be higher, given there's p-hacking and there's a real pressure to get your PhD. So what can we do to reduce the risk? And we talk about in hypothesis testing is a power of the hypothesis, and it makes sense. I've only done an x of 10 and a y of 20. What happens if I increase those numbers? I'm likely to get a bigger value. So put in x and y of 100 and 200. And I can rerun the t-test. And as you can see, the degrees of freedom's gone up. There's much more data in this. You could imagine this as if I took a very small data set, it's probably like that. And then if I add more data to it, it gets like that. Ooh. But the distance between those two values is greater with more information. So you manage to reduce your risk by bringing in more information and bigger tests. So as the DF, the degrees of frequency, goes past 30, it's almost certain that your sample size is equal to the population. And that's a good way of thinking about how big a sample size for a test you should have. There's an idea that you should have at least 10 false values in any test, but I'd go into that later, or try and if I do a video on that, I'll have to think about it. But as you can see, the p-value in this is -16. It's tiny. Now, this brings in the concept of type 1 and type 2 errors. Type 1 error is where you accept your hypothesis and reject the null hypothesis, even though that's wrong. And you would say that's really bad in something like medicine, but that's probably less bad if you're just doing a quick analysis of what is the hypothesis in a data mining package of this being true, for somebody to come along and check later. So your idea of your type 1 and type 2 errors is type 1 error is when you accept your hypothesis and reject the null, and type 2 is the opposite, and it's the risk you have of doing that given what you know of your situation. And moving on, what we just did was actually a student test, because if you notice, we've added in this variable of var.equals true. And what that will do is it'll make it a student t-test. And there are different types of hypothesis tests. The student t-test really focuses on if two sample sizes have the same variable. It's in the name, variable equals true. You can do a equals false, which was the Welch test we did last time. And you can see it's the same, but if you had two data sets and you didn't think the variance within the data was the same, you wouldn't do that. You can do something called the Levene test if you're not sure that your two sample sizes variance are the same. And you can finally do a Wilcox test if you think you've got very unequal data, and they call it parametric. And I'm not going to go into explaining what that means right now in this lesson, because that's a different subject, but you can sort of see you've got slightly different values out of that, and you would get better values out of doing the right hypothesis test for your sample size. And then as a final point, you can use these degrees of freedom. You can do a lookup on a CFT table, because what you've got to think about is, in reality, and guru99.com provided this picture on their website, which I am completely using, but it gives you an idea of that there's a CFT table, and you can look up based on the standard deviation and get an even more accurate level of confidence. And as you see here, it's got a -2048404. And if we look at our t-value up here, if the t-value is lower than that, you probably should accept your hypothesis. And that QT value takes into account the DF, the degrees of freedom. So you can basically do a quick check after it, based not only on the p-value. Now, that was a real quick run through. I hope it clarifies some things about hypothesis testing. I hope you have a good day. Bye.